So my talk today is theory work with I and Lazarsfeld. So to begin, I'm going to give you a number of motivation for the problems that we look at. I'm going to go through two basic motivation. One is a classical one, and one is more tied to a little bit closer tied to recent studies. So let's fix a number of notation that I'm going to use through the talk. S is going to be the coordinate ring of a R-dimensional projective varieties, and we will always work over the complex numbers. M is going to be the irrelevant ideals. We're going to start with a bunch of homogeneous polynomials of degree d0 up to dp, and we're going to order the degrees of these polynomials in the non-increasing order. And J is going to be the ideal generated by these polynomials, and X is going to be the zero set of J. Of course, being a variety inside Pn, we can have many ideals cut out the same variety, and among them, we're going to let I of X be the saturated ideals that define this variety X. Okay, so the first motivations for our problem comes from an old theorem of Macaulay. And basically, when the variety that we start with is empty, in other words, the ideal J is primary to the irrelevant ideals, then we all know that starting from high enough degrees, this ideal is going to agree with the polynomial ring. So the question, the natural question is how large one has to go to get these equalities. And an old theorem of Macaulay basically say in this situation, as long as t is bigger than the sum of d0 up to dr minus r, then we have this equalities. And notice that here we only go up to r, even though the ideal might be generated by more than r plus 1 elements. In the case that we have less number of generators, then we can think about the generating degrees being 0 afterward. A slightly less well-known results basically works for powers of J as well. So power of J also is M primary. So and the theorem say that the power of J will agree with the polynomial ring starting from T being at least A of D0 plus D1 up to dr minus R. So of course here we see that the rows of the degrees are not symmetric. So D0 is the dominating term. So usually when I give a talk to, at least at Tulane, when we have graduate students, I often give an exercise. And so this could be an exercise for you to work on in case you get bored during my talk. So the exercise is to show that in the case that P is the same as R, so we have the right number of equations, there are examples showing that these bounds are best possible. So from going from this theorem of Macaulay, the natural question is what happens when the variety that we start with is non-empty? Are there any similar bounds in the general situation? Now, of course, in the general situation, when X is non-empty, we don't expect J to contain any power of M or to be M primary. So Macaulay's result should be viewed as a bound on the saturation degree of J and of its powers, and that's because when X is empty, J is M primary. That's the same as saying that the saturation of J is the same as the polynomial ring itself. So let me just briefly recall the notion of saturation and saturation degree. So we start with any homogeneous ideal. The saturation is just obtained by taking out the M primary components of the ideal. So either we column by M to infinity, or if we know the primary decomposition of I, then we just throw away the M primary piece in that primary decomposition. And it's known that sat, which is a saturation of I and I, agree from a high enough powers onward, and the saturation degree is defined to be the least or the minimal degree starting from where the saturation of I and I agrees. Okay, so let's just look at a very random example. So here in this case, I start with an ideal, and I know that it has these primary decompositions. And so to compute the saturation, all I need to do is to throw away this M primary components. And so the saturation is obtained by this. And one can check using Macaulay too that I sats and I are different from degree up to degree 12, and then at degree 13 they start to be the same. So the saturation degree in this case is 13. Okay, so the problem arising from Macaulay's theorems is the following. So we start with any homogeneous ideal generated in degree where we order the degree in non-increasing order, and suppose that X is the variety cut out by this ideal. Then can we find linear bounds for saturation for the saturation degree of powers of J in terms of its generating degree? So let me give you an example where this is possible. So let's start with any linear forms and a hyperplane in Pn given by these linear forms. Now this hyperplane is also cut out by the ideal generated by F0 up to Fr, where Fi is just obtained by multiplying L with the d minus first power of xi. So in this case, of course, J and the ideal generated by this linear form define the same variety. So the saturation of J is the same as L. And it's not very hard to compute the saturation degree of J. Is going to be R plus 1 times D minus 2R. If we look at the Macaulay bounds, the bounds should have been R plus 1 times D minus R. So yes, it is sort of close enough to the Macaulay bound. So one can hope to be that there are some linear bounds for the saturation degree of powers of power of J. However, there's also a simple example where this is not possible. This is an example in the Cavaliers' thesis a while back, and in this example, he looked at a very simple ideal generated by x to the d, y to the d, x to the z to the d minus 1, y w to the d minus 1. Then in this case, asymptotically, the saturation of J is the same as d squared. So there's no hope to get a linear bound for the saturation degree in terms of the generating degrees. So one need to modify these Macaulay problems a little bit by putting, well, one could modify Macaulay's problem a little bit by putting extra conditions on the variety X. And for us, we assume that X is going to be a smooth variety. So we state the problem as follows. We start with a homogeneous ideal given generating degrees, and we assume that the variety cut out by these polynomials or by this ideal is a smooth variety inside PR, and the question is to find linear bounds for the saturation degree of powers of this ideal in terms of the generating degree. Now, so why do we want to add this smoothness conditions? It makes sense also for us from another point of view is there has been a lot of work on the symbolic powers of ideals in commutative algebra in recent years, and when X, at least when X is smooth, the saturation of the defining ideal or powers of defining ideal of X is actually the same as the symbolic powers of X. So in this case, finding the saturation or bound for the saturation degree is also the same as finding bound for degrees starting from which powers of the defining ideal of X and its symbolic powers agree. Okay, so let me stop here for a minute to see if you have any questions so far before we move on to the next motivation. Okay, good. So the next motivation, which is closer tied to my my work in the past, is about regularity of powers of ideals and ideal shift. So we're going to start with a power, and then with an ideal, homogeneous ideal J, and we're going to let script J be its corresponding ideal shift. Now the regularity has been studied extensively by many authors in many years, and unfortunately there are two different notions of regularities existing in literature that actually at times cause confusion, and while writing this paper we actually discover a number of papers where, because of the confusion between these two notions of regularity, they end up getting wrong results. So regularity initially was defined for a coherent shift. So for us, because I only talk about ideals, I'm going to restrict myself to ideal shift and ideals instead of coherent shift and modules. So regularity, or an ideal shift I, is defined to is said to be M regular if we have these vanishing conditions for twist of the ideal shift. And in terms of algebra, the ideal J is said to be M regular if we have the vanishing condition for certain degrees of the local cohomology of J with respect to the maximum ideal. And the regularity is defined to be the minimal M such that either the ideal shift itself is M regular or the ideal itself is M regular. So the relationship between these two notions come very clearly from the Serre-Grothendieck correspondence, which give a short exact sequence and isomorphisms when I is bigger than 0. So from this isomorphism, for example, one can see very easily that all this vanishing condition translate to this vanishing condition over here. The difference between the two notions lies at H0 and H1 of J. So when one talk about regularity in terms of ideal shift or in terms of shift cohomology, we do not take care of this H0 and H1. And when we talk about the regularity from the algebraic perspective or from local cohomology, we actually answer one vanishing condition on H0 and H1. So this is the difference between regularity in terms of shift and regularity in terms of modules. And the difference lies at in H0 and H1, and the vanishing of H0 and H1 is in fact it lies in this map where you map J to the section to the sections of J. So it's about when this map is an isomorphism. Okay, so so here is the situation we start with. We start with a homogeneous ideal with given collection of generating degrees. X is the variety cut out by these ideals, and we're going to assume that this is a smooth variety. And furthermore, I'm going to let E denotes its codimension. Then the ideal J and the defining ideal of X will have the same saturations, and they define the same ideal shift. So the motivations for the study of regularity of powers of ideals and of ideal shifts come from a very nice result of Bertram, I, and Lazarsfeld in the 90s, in which they proved that under our setting here, the higher cohomology of the 8th power of the ideal shift of X twisted by K is always 0 for all K bigger than or equal to a d0 plus d1 plus up to de minus 1 minus r. So here you can see that one can only one only need to go up to the codimension minus 1. On the other hand, in Macaulay's theorem, one need to go up to r. right? So that's the first difference between this result and Macaulay's theorem. Particularly, by definition, this say that the regularity of the eighth power of the ideal sheaf of X is bounded by these linear forms or linear functions, a times d0 plus d1 plus up to de minus 1 minus e. On the other hand, for ideal, there's a result by Kukoski, Herzog, and Chung independently. Kodialam, this should be Kodialam. In 1999, where they proved that for any ideal, homogeneous ideal J, if you look at the regularity of the eighth power of this ideal, it is asymptotically a linear function. In other words, there exists constant so that the regularity of J to the A is A times D plus C for all A big in F. So both of these, since both of these results, there have been a lot of work trying to understand, for example, what is these conditions D? What are these conditions D and C? The constants or constant D and C. Constant D is actually very well understood from reduction theory, but constant C is actually much harder. After a series of work by Eisenberg, Harris, and eventually by Max Scharding, they were able to basically see this constant C by a collection of local data through a projection map from the blowup of the given variety. But this result, on one hand, is very nice in the sense that it says that the regularity is asymptotic linear functions. On the other hand, it's not very easy to determine starting from which value A this function is going to be linear. So in practice, this A could be very big. So if one wants to get some kind of estimates for the regularity for small power of A, that's not an easy test. So a question that I was interested in is to find maybe not the exact linear form, but to find some sort of linear bounds for the regularity of J to the A that somewhat resemble this linear bound here, but works for all power A. So that's the one question that I'm interested in, is to explicitly give bounds for regularity of powers of J, where which hold for all value A and in terms of the generating degree of J. Now, one thing we know from the CAAG-Rothernick correspondence is that the regularity of the ideal is the max of the regularity of the ideal sheaf and the saturation degree. So when we give the a linear bound for the saturation degree of the powers, and at the same time we know a linear bound for the power of the ideal sheaf by the results of Bertram and Lazarsfeld, we automatically get a linear bound for the regularity of the power of the ideal itself. So it will answer this question by looking at the saturation degree of power of this ideal. So the question now we eventually look at is, we start with an ideal, we order the...
Sorry, can I ask something, because I got a little bit lost now?
Yes, go ahead, please.
So when you have a bound, a linear bound, not even bound, formula for high enough A, right, then just by making C big enough, it will work for all A. Why are you not happy with that?
Yes, but the problem is that in this result, the problem is, for one, if you want to get a good linear bound, you have to include the regularity for all small enough power A, right, until it reaches the linear forms. But the problem is that this value A, the minimal value A, where the regularity becomes linear, could be very big, and it's not well understood at all. So in practice, given an ideal, it's hard to determine how far you have to go to get a good estimate. So that's why we want to get some sort of linear bound that works right from right from the beginning. Does it answer your question, Dan?
Well, not really, because can you not just make it work for these finally many A's by taking C much bigger?
Yes, yeah. I mean, as I said, it works, right? You can take so for example, here you can take C. You can take like max of this C and then regularity of J to the B, where
Right.
B is smaller than or equal to A0, right? Something like that. But the problem is that uh,
Right.
this constant C is not well understood, and even in many cases one
Okay.
can somehow estimate this constant C by various methods, but
Yeah.
this is not easy to find because we don't understand this constant
Yeah.
A0 either, right?
So when you're
Thank you.
saying you want a bound, you mean to say a bound in which I know all the coefficients, basically.
Right. Yeah, I want to have some sort of explicit bound that
Okay.
I
Okay.
can't use to give a good estimate for this
Okay.
guy. Yes, thank you. And
Gotcha.
that's a
Gotcha.
great question. Okay, so yeah, so here the question, so the problem that we end up is to again start with homogeneous ideal with given generating degrees. We start with the variety cut out by this ideal and assume that this variety is smooth, and we are interested in finding linear bounds for the saturation degree of its powers in terms of the generating degrees. Okay, any other questions before I continue? Okay. Okay, so now let me state our theorem. So the first theorem we prove is that if under the assumptions that I mentioned, then we can bound the saturation degree of J to the A above by A d0 plus d1 plus dr minus r. So this is exactly the same as the bound that we saw in Macaulay's theorem. So we prove that in this case it still works. Now, this is a very simple example where you take 3 coordinate points. The ideal is easy to figure out. In this case, d0 equal to d1 equal to d2 equal to 2. So, and then one can compute the actual saturation degree of the 8th power of the ideal shift of x, and that happened to be 2a. The bound that we get here is 2a plus 2. So in some way it is close, but it's not exact, right? It's not really sharp. So one could ask, so is there any kind of bounds that is like a times something, right? So maybe linear in that form, in that sense, like it regular saturation degree of J to the A less than a times some quantity, and we in that sense we can we also have a result, but it only works when x is a curve. So we prove that if x is a smooth curve, then for OA the saturation degree of the 8th power of the ideal of the defining ideal of x is bounded above by a times the regularity of the ideal shift. And when I write the regularity of the ideal shift, I really mean the geometric regularity, because the algebraic regularity already includes the saturation degree, so there's no point of including it on the right hand side. So this bound is actually quite well known for points. For point, the saturation degree is just the regularity of the ideal, and it's known by Giomita, Giuliano, Peter Loud, and then reproved by Chandler and extended by Siedmund. We don't know if this bound still valid when x is not necessarily of dimension 1. We don't see any reason why it's not true. It's just that our techniques can only handle the case of curve. So we don't know what to expect with this question, whether or not this bound is still true, is still valid in any dimension.
Do you know anything for surfaces? Or
So yeah, so we do have some results in the surfaces that we expect it to be true. That's why we expect it to be true. Yes.
And no counterexamples.
No counterexample. Yeah, yes. Yeah, the problem is that doing computation is not very easy in this case, especially you do definitely have to require that x to be smooth. So it's not easy to start with to run example because you have to you run example, you have to start with a bunch of equations, then you have to test whether or not the variety is smooth. That's not an easy thing to do in Macaulay 2. But in the example that we know of, when we run, this bound seems to work. So I'll put this as a question here. Okay, so let me now tell you about the method of that we use to prove these theorems. And it turned out that the method that we use are very standard method in algebra, and it just happened that somehow everything pieces together to make the argument work in a nice way. Okay, so let's let me briefly go through ideals and tools that we use. So first, we start with an ideal generated by a bunch of polynomials of given degree d0 up to dp. This is the ideal sheaf. Once you know the generating degree of the ideal, you have a surjective morphism from of sheaves of this form. And when you have such a morphism, you can look at the tensor product and obtain a surjective morphism of this is the asymmetric sheaves of U0, and this is just the 8th power of script J. So so for any any t here, when I do the twist by t, algebraically it just means I'm focusing on the degree t, right? So it's really nothing new here. I'm just looking at this and I twist by t, twist this by t. That's the same as looking at degree t. And because of how this U0 is defined, it's very easy to see that the image of this map, when you look at the corresponding map of sections, you get exactly the degree t piece of j to the a. Now, of course, this is subjective. Doesn't mean that this map on section is subjective. In fact, it's often not subjective, because the right-hand side, this quantity here, is the same as the degree t piece of the saturation of j to the a. So the question we're looking at is when we have this equality, it's very much the same as saying that when this map is surjective. So in algebra, in order to determine when maps between section is between sections is surjective, a very standard tool is to fit this into a complex, right? So if one can fit, so you start with say coherent sheaf here, and if you can fit this sheaf in a complex in which we can control the regularity of its terms and the dimension or the supporting dimension of its homology, then one can get surjectivity for sections of the last map. So this is a standard technique. So so the task or the strategy that we use here is, first we're going to fit this 8th power of script J into some complex L, where we can control the regularity of L, and we can control the supporting dimension of the homology in L. Particularly, for example, if L is an exact complex, then all homology are gone. So this condition is satisfied automatically. So the idea is, well, you start with j to the a, can we say get a minimum free resolutions for it? If you get a resolution for it, then we get an exact sequence, and that condition is satisfied. And if we get a resolution whose term can be, or the regularity of whose term can be controlled, then we are done, basically. So that's the task at hand, right? So how would we go in doing this? Now we know a number of complex resolving power of an ideal, and using that we obtain the bound that I stated before. So for simplicity, we're going to denote P be any smooth variety. In this, in later on, P is going to be the PR that we the ambient space that we start with. V is going to be a rank E vector bundle on P, this is just the U0 that you have seen before. And suppose that there's a map between vector bundles from V to the structure shift of P, whose image is an ideal shift. Okay, and that define a subscheme Z inside this projective variety or projective space later on. Now later on, X is going to be Z here is going to be our X. This is going to be the ideal shift of X. Okay. And we will let SA 1 to the power k minus 1 be the shear power of V corresponding to the partition A1111 where you have k minus 1 number 1 here. Then Bushbauer and Eisenberg in 75 show that there's a complex given by this shear power of V that maps surjectively into the A power of this ideal shift I. And furthermore, this complex is a resolution or is it's exact if either this map is surjective. In other words, this ideal shift I is just the structure shift itself, or if Z is a complete intersection. So in applying these results, we are going to look at a case where this is a surjective map, right? Where this I is just the structure shift. Okay. So here we're going to go back to our situation. P is going to be our ambient space. V is going to be this U0 that we start with. And this guy, now the shear factor of V is going to be the shear power of this direct sum. And because of the nature of this, how this is defined, one can see that it consists of, or it is a direct sum of line bundles of degree given, or at least this quantity. So and one of them appear with that degrees. So the regularity of all these terms are actually well determined. So if one look at this complex, we know the regularity of all these terms. So in our strategy, if we know this complex is exact, then we are basically done, right? And by Bushbauer and Eisenberg, we know that this complex is exact if this map is surjective, or if X is a complete Z is a complete intersection. Now, in general, unfortunately, we do not know if this complex is exact. So we have to control the supporting dimension of homology of shift resulting in this Bushbauer-Eisenberg complex. And this turned out to be a very difficult problem. So generally, another very common method that we see in algebra is if you fall into a situation where things are not very nice, and you want, then you just blow it up, make things nicer. And so this is exactly the next step in our method. So again, I'm going to start with PR being the ambient space. U0 now is the V, the vector bundle V that I mentioned before, mapped to the ideal shift of X. And then I'm going to denote by P prime the blow up of PR at X. So it's going to map down to PR, of course. Let E be the exception divisor of this blow up, and H be the pullback of a general hyperplane in P. Then in this case, Ix times OP prime is just OP prime twisted by negative of the exception divisor, and you can we can pull back this shift U0. So this map now, if we pull back, it's going to give us this map epsilon prime from U0 prime to OP prime twisted by negative E. So if you twist by E, you basically get E prime being a map from U0 prime tensor with OP prime E to OP prime. So this is the case where we can apply the Bushbauer-Eisenberg construction, knowing that the right-hand side is the whole structure shift, knowing that the sequence that we're going to get is going to be exact. The quantity that we are interested in is, of course, is 0 of twists of the power of the ideal shift. In this case, you can also pull back to P prime, and this is the same as S0 of P prime OP prime twisted by TH minus AE. And so one can obtain this by looking at this guy using the Buchbauer-Eisenberg complex, then twist by TH minus AE. And so if we do that, then we get this sequence, which in this case, thanks to the Buchbauer-Eisenberg results, we know that this sequence is an exact sequence. Right? So to go back down, so this is the blow up. To go back down, one need to really see what happened to all this guy when we push down through pi. So the question is really about when the higher image of this guy vanish. Now, all this quantity, when you push down, you get corresponding powers of V, show power of V. For all this quantity, while the TH is going to push down and get twist by T downstairs, the only remaining or the only difficult or matter terms are what happened to this OP prime and some copy of E. So we need to figure out what this guy, the higher direct image of this guy are and when they vanish. And thankfully, that can be done at least for the negative copy of A. By definition, it's just the power of the ideal sheaf when J is 0 or 0 otherwise. For the positive copy of this guy, what we can do is we can prove. So you don't have to pay attention to this. What we can prove is that this is almost always 0, except when J is 0, which is what we expect to get, and when J is E minus 1, the codimension minus 1. So the term that gives us problem is the higher direct image at power E minus 1. But for that, we can also prove that, well, either you get 0, even for the power E minus 1, or when big enough for big enough A, you don't know if you get 0 or not. At least we can get a filtration of this guy whose successive quotients is of the form sk of n tensor determinant of n when n is normal bundle of x. And so that allows us to make use of results that I and Lazarsfeld know a while back. So even though this theorem is in our paper, it's actually known by I and Lazarsfeld a long time ago, but they didn't have any use for it. Somehow it fit well with what we need this time and give us what we want. And they prove that if we start with a smooth variety of dimension n inside PR, then we have this vanishing conditions. So this kind of vanishing condition was very popular in the 90s, and there's results by Manival and Schneider and Zint in the 90s proving similar kind of vanishing conditions. Unfortunately, we also checked their results, and their results do not imply what we want. So we really have to go, or fortunately, we have this. We know these vanishing conditions, and we get what we want. Okay, so basically the idea is if you start with a smooth variety, you look at its normal bundle, then higher cohomology of a k-symmetric algebra of n, tensor with determinant of n, and high enough twist of the structure sheaf is going to be 0. Where high enough, I mean, is at least R, negative R. Okay? So using this, now everything fit together and tell us that the Buchbauer-Eisenberg sequence upstairs is exact, where you can control everything, and even when you push down, you still can control everything, and that's why we get this result. For the other results, so here this is the result that I mentioned about the curve. What we use to prove is to start with a very different complex. So instead of starting with the surjective map defined by or given naturally by the General degree of the ideal, and then take the symmetric algebra of that map, or take the Bush-Bauer-Eisenwood complex of that map, we start with any resolutions of the ideal sheaf, right? Any locally free resolution of the ideal sheaf, and then we make use of a complex called constructed by Wyman in the 70s, and try to work with terms of that complex. So particularly, again, the task at hand is to resolve the 8th power of the ideal sheaf. And what we do is, well, let's just start with any locally free resolution of this, right? Now, because this is a locally free resolution of the ideal sheaf of X, so one know that the regularity of its terms is controlled by the regularity of the ideal sheaf of X. So we know these conditions. Then Wyman say that if you start with such a resolution for Ix, then one can construct a complex that maps to the 8th power of Ix, in which the ith term is obtained in this way. So here we're going to take either symmetric powers or exterior power of terms inside this resolution of Ix. So for even index, we take the symmetric power, and for odd index, we take the exterior power. And for example, for the first few terms, it's easy to write down. So you start with ax to the power a, you go to the symmetric, the asymmetric power of u0 still. The next term is just the a minus first symmetric power of u0 with u1. So u1 is the next term in your resolution of ax. The next term will consist of two terms where you take symmetric of power of u0 and then exterior power of u1, or you take symmetric power of u0 and then you take also symmetric power of u2, right? So remember that for even index you get symmetric power, and for odd index you get exterior power. Of course, it go on to L3 and L4, etc. But the later terms are a lot more complicated and involves more terms. But what Wayman was able to prove is that away from X, this sequence is always exact. So that allows us to, again, first, because all the terms here are coming from symmetric tensor and exterior tensor, we knowing the regularity of each of the u0, u1, u2, etc., we can estimate the regularity of all these terms. So we can actually control the regularity of each term in this sequence. So knowing is exact away from X basically means that away from X the homology are 0. So the homology basically so that basically says the homology is supported in X, and that's why if X is of dimension 1, we can work with we can make use of the standard method to see when when the map of the section associated to this map is surjective. In fact, we prove that, well, if we forget about the later term, just look at the first few terms here, it's always exact, right? And that allows us, at least in dimension 1, to do diagram chasing, just the standard techniques. You have a long exact sequence, you break into short exact sequences, and chase through those short exact sequences. So with just this, it's already enough to prove that the section here is the map of the section here is surjective. So unfortunately, these techniques only work because we have a curve. We know that the dimension of X is 1. For higher dimension, we would have to continue to go into this term, and unfortunately, in general, we don't know if this. In general, this sequence is not necessarily exact, or at least this part is not necessarily exact, and so it doesn't work for our technique doesn't work when the dimension of the varieties is higher than 1. Okay, thank you so much for your attention, and I'm ready to take any questions if you have.
Thank you, Tai.
Thank you. A quick question about hypersurfaces. I mean, it seems like for hypersurfaces, you can calculate those degree for the saturation ideals and also the M regularity, right? So there, do you have any like results?
You mean let's see. I mean this situation here. Oh, hypersurface, not hyperplane. Okay,
I mean,
hypersurface.
yeah, hypersurface. Let's say you have a hypersurface of degree D, right? So
Yeah, I think if okay, so yes, so if you can't play the same game, right? If you have a hypersurface of degree E, and then if you are you forming the same kind of ideals, or you just take the ideal F itself?
mhm.
Now, if you take the ideal F itself, it's let me see. If you take the ideal F itself, and then you look at I think this case is kind of known, right? Everything is known. If you look at F to the A, I think this is already saturated, right? So you can't play. So if you just look at the ideal F itself, everything is known. So you can play the game like you look at the different ideals J, where J is given by you take F and multiply with a bunch of high enough powers of its I. Then yes, you can, in that case you can also compute the saturation degree.
Yeah, and then I guess there probably you also have the same formula, right? I mean,
yes,
yeah.
Yes. Yes. Yeah.
Sounds good.
Thank you.
I just noticed a paper by Takumi Murayama today. I think the paper gives uniform bounds on the symbolic powers over regular local rings using some perfectoid ideas and those kind of things.
Uniform bound of I'm sorry, of what in
The
the
symbolic powers of I mean over regular local rings. I don't know if any
uniform bound of the regularity or of what, of the symbolic bound.
just the symbolic powers, not the regularity.
Oh.
But I don't know. I mean, I just noticed this paper today. Maybe some of the techniques will help with some of the questions.
I will take a look at that. Can you give me the names again?
The name says uniform bounds on symbolic powers in regular rings, and the paper is by Takumi Murayama.
Oh, okay.
It just appeared on arXiv, I think today or yesterday.
Oh, okay. I'll take a look at this. Thank you. Thank you. Yeah, it'll be interesting to see what else is known.
Yeah.
So are you guys planning on working on surfaces? You trying to find the different techniques from the one with the curves?
So we actually did prove. I mean, we did work on services, and we get some results, but not too strong, unfortunately. Let's see. Let's see if you. Let's say we can estimate the regularity of the 8th power of the ideal sheaf of X in terms of the regularity of the ideal sheaf itself. So we get something like very similar to the bound for curves. So we get something like we get something like this. But instead of over here, instead we have something like regularity of the ideal sheaf of x to the power a. Right. So it's not exactly the same as this, but it's basically say that what one can hope for. Anyway, as I said, because the techniques that we use is very specifically tied to a very particular complex, and that complex, when you go beyond the first or the second terms, you get a lot very complicated very quickly. So we don't know what to do. So I'm hoping that if people who work in resolution know how to resolve power of an ideal or an ideal sheaf, if they have different kind of complexes, then that will give new bounds for this kind of questions.
But that is a very nice blending between the commutative algebra, algebraic geometry, and the homological algebra. It feels like everything is in it. So we can.
Yeah, so I mean, techniques are, I mean, the methods are very, very straightforward, right? It's all the common method that we all use. But I mean, we are lucky in this sense that, in the sense that eventually what we need happen to be known before, so it fits together and works nicely. So.